colleagues, can we call the session to order? Start now. Please have a seat. So the first talk will be on Venus Plus. This will be Joe Coelho. Will tell us about that. Please, Joe.
Okay, thank you for the invitation. So I'm going to talk about the latest from Minos and from Minos Plus as well. So I'll start with a description of the NUMI beam, which is where Minos is. So the NUMI beam is currently already running at 350 kilowatts, but it's capable of producing a 700 kilowatts beam that we're working towards it. So in the past, the NUMI beam was running in this low energy mode, where you can see the yellow curve here. That's where Minos was taking data, and about a year and a half ago, we switched to this medium energy beam, which at the 14 millirad angle that the NOVA detector is, you get an energy that is about where the oscillation peak is expected to be. But that means that now the Minos detectors will see a broader spectrum at higher energies. And so this will be good for us to test other theories, other models. So basically, we have protons that are being accelerated here from the LINAC, and then they go through first accelerator, the booster, and then they go to the main injector, hit a target, and then the pions and kaons decay here in a decay pipe, and then the neutrinos go through the Minos near detector and then to the far detector, which is 735 kilometers from Fermilab here in northern Minnesota. So the NUMI beam has been very successful, and we've taken a lot of protons on target already. So we've reached over 20 times 10 to 20 POT delivered, and since the change to new beam energies, we've collected this amount of data, which is about 4.6 times 10 to 20 POT, so we already have a considerable amount of data to show. In the beginning, there were accelerator upgrades, and so the intensity sort of dropped from the last intensity that we saw in Minos, but now it's been ramping up, and we're already about at the same scale, and right now people are trying to ramp it up to 400, and then we'll have the highest intensity that we've ever had. So going on to the Minos Plus experiment. So the Minos Plus detectors are magnetized steel scintillator tracking calorimeters. You've got here a picture of the far detector. The near detector is about 1 kiloton. The far detector is 5.4 kilotons, or as with my new favorite metric, it's about 28 blue whales. So basically you have planes of steel alternating with scintillator strips, and the planes of scintillator have strips that are orthogonal between one another, and so you can reconstruct tracks in 3D tracks with this. And so the events look sort of like this. If you have a muon neutrino interacting, you're going to see a CC interaction will have the muon track here, and then some hadronic activity. And if you have a nu E, you get some sort of electromagnetic shower that looks like this. And if you have an NC event, you get mostly hadronic energy, and it's more spread out. But it's not always easy to distinguish these two, especially if you have a pi zero here or something that has electromagnetic component. And so basically our job is to try to identify these three topologies and separate the three types of events that we can see. So our goal is to measure neutrino oscillations or any type of neutrino flavor transition. We can do that by using the beam. So you have the near detector and far detector, and basically you can compare the information in these two detectors. And the near detector we expect with standard oscillations, no oscillation at all. And in the far detector you expect, for example, for muon disappearance, you can see at low energies we expect this dip, and most of it is going here to tau neutrinos, but there's some nu E appearance as well. And we can do then with this, we can do nu mu disappearance, we can do nu E appearance, even though this is small. Tau appearance is kind of hard because there's a lot of background, but we're looking into it now that we have a more high energy beam. But anyway, we can also look at NCs, and then based on the sum of nu E, nu mu, and nu tau, we can infer what the nu tau component is by just looking at the NCs. And of course, we can also look at atmospheric neutrinos, and those will go through larger distances and through a lot of matter, and so they give us some power in terms of matter effects to distinguish between things like mass hierarchy and octant of theta 2-3. So we've shown from Minos an analysis of all the neutrino data that we took in the Minos era. We have events from nu mu disappearance, from nu E appearance. We have samples with neutrinos and antineutrinos. We have beam neutrinos and atmospheric neutrinos. And into this, we already added about 10.8 kiloton years of atmospheric data in the Minos Plus era, which is a 28% increase from what we had with Minos. And with this, we're able to get these contours that you've seen in talks before. And basically, this is the best measurement of delta m square 3.2 and competitive measurements in sine squared theta 2-3. So we get about 3.8% precision. But really, what we're interested mostly now in this new era of Minos Plus is with exotic phenomena, things that are different from standard oscillations. So one of them that we've released results with the Minos data so far is sterile neutrinos. So we're looking at a model with one extra neutrino mass eigenstate, and basically you get some mixing of that, which is mostly a sterile neutrino but has some mixing to the active neutrinos as well. And basically we expect extra distortions in either of the detectors. So if we have a difference in the mass of the nu4 and nu3 that is very small, or at least it's small compared to about half an electronvolt squared, you get distortions here in the FAR detector, which we're looking for things that are usually high energy in the FAR detector. If this is about half electronvolt squared, then you don't expect distortions in either detector from this type of oscillation, but you expect sort of a deficit in the FAR detector compared to the NEAR detector. And then if the delta m square is much larger than 0.5 electron volts, you start seeing oscillations in the NEAR detector. But in that case, you also get the oscillations smeared because you have to consider that the neutrinos are produced throughout the decay pipe. And so here's a plot of where the pion or kaon decayed to form the neutrinos. And you can see that it's peaked at close to the target, but you do have a distribution that goes all the way to the end of the decay pipe. So what we do is we look at the ratio of the NEAR and FAR detectors, and we look for any discrepancy from the normal three-flavor oscillations that could be explained by an extra neutrino mass eigenstate. And basically we see no evidence of active to stereo neutrino mixing, which indicates that the nu mu's must actually be transforming into nu taus. In our NC sample here, we're actually having some nu E contamination because we're only really selecting things that are showers in the detector, and so we don't really separate between nu E's and NC's. But as you can see, the agreement is pretty good with the three-flavor prediction. And from that, we can extract contours and exclude regions of the parameter space in this new angle theta 24, and depending on the delta m squared 4,3. And so you can see that we exclude now a large region that was unexplored before, and we can use that in combination with reactor experiments, and in particular we took an example with Bouguer and convert this nu mu disappearance nu mu disappearance plus nu e disappearance into an expectation for nu mu to nu e. Because of course if nu mu's are going to nu e, then nu mu's must be disappearing, and because you can reverse this with some CP violation, nu e's must be disappearing as well. And so when you combine both of those, you get this red exclusion here, which excludes most of the LS and D mini boon and only leaves some higher energy, which is actually, there are other experiments that disfavor this region as well. So another model that we've looked into with MINOS is looking for Lorentz and CPT violation. So basically we look at this standard model extension and it gives you some terms that provide CPT violation, and that can lead to transitions between neutrinos and antineutrinos. And so basically you expect an excess here of positive charged muons in the negative charged neutrino beam. And but since we don't observe that excess, we can set limits, and we've got limits of the order of 10 to minus 23 in some of these parameters. There are a lot of these SME parameters, but these ones that we can probe, we can improve the limits by 7 orders of magnitude over previous constraints. And finally, for MINOS, we've also looked at the possibility of extra interactions that will change the matter effects and change, therefore, the oscillation pattern. And you can look at the difference between neutrinos and antineutrinos will be important here because the matter effects will be different. And so if you look at nu mu disappearance, you get this effective parameter epsilon mu tau that we can constrain. And if you look at nu e appearance, we can constrain this other parameter epsilon e tau. And basically we see no evidence for these types of non-standard interactions. And we can set limits, and so here is a contour for the nu mu disappearance, and you can see that it's consistent with 0. And for the nu e appearance, you can see the same thing, it's still consistent with 0. But here we have some sensitivity which is much better than other experiments, but it's still of order 1, which is basically of order of the standard interaction that we have from neutrinos and electrons. So moving on now to MINOS plus. So now we have started taking data from the beam with MINOS plus. We've looked at preliminary data from MINOS plus just to check whether the oscillation pattern was consistent with what we saw in MINOS, and you can see that it was. And so we've already taken about 30% more POT with respect to what we had in MINOS, which is about 3 times what you see here that we've looked at. So there's new results coming soon, but here you can see that all of this agrees with what we've measured before. And with this high energy beam, we will be able to probe new physics phenomena that happen in this energy scale between 5 and 10 GeV with much better statistics. So we're going to fill up this sort of region and look for anything different that might be happening there. So in terms of future sensitivity, we can look at, for example, sterile neutrinos. So we've already done pretty well with the neutrino mode, looking for sterile neutrinos, but MINOS plus can extend that a bit. But especially if we get to run in antineutrino mode, Here's what you expect with just the MINOS data in terms of constraints using antineutrinos, and then we can move to the red line if you run for about 4.5 times 10 to 20 POT, so that would be a big improvement and would be really good. And one important thing is that if we measure antineutrinos, and especially with the NC sample, we will be sensitive to CP violation here, because basically this is a new sterile transition. But in any case, we can also test CPT if things are different. One other model that we've looked at is sterile neutrinos again, but the possibility of these sterile neutrinos traveling through an extra dimension that is relatively large. And basically you probe the size of the largest extra dimension that might exist, and this depends on the smallest neutrino mass as well. So we plot contours that are based on the smallest neutrino mass and the size of the extra dimension. And basically we expect similar probabilities as you see in the sterile neutrinos that I showed before. And we can probe with this sort of half a micrometer size, and that's about an order of magnitude better than other constraints, but then this is very model dependent. And then with MINOS Plus, we can improve that in about 3 years to 0.4 micrometers. Another thing that we're looking into is using UE appearance to check for sterile neutrino induced oscillations. So we can get with this sensitivity that is similar to what Icarus and Opera has shown, and so this would be something exciting, which is a more direct comparison with LSND and Miniboon. But this is a quite difficult measurement for us because it will have interference with the 3 flavor oscillation turbs. And the last thing I want to show is that even though we're not really doing standard oscillations as the main goal of MINOS Plus, we still have something to contribute, and by late this year, if we combine the results of NOVA and MINOS Plus, you can expect a sensitivity that improves from the NOVA only contours, which is the dashed one, to the solid lines here, which combine NOVA and MINOS Plus. So you get a big improvement from what NOVA can do on its own for this year. So in summary, MINOS has done very well in the past, and we've made world-leading measurements of neutrino oscillations. And now with this new era of MINOS Plus, we're going to probe new physics, and we're excited that new results will be coming soon. And we already have 4.6 times 10 to 20 POT collected. So stay tuned for new results.
Thank you very much. Discussion, questions, comments? Yes.
Could you show us some comparison between data and Monte Carlo without any correction at the near detector only?
Well, I don't have that here. So that's something that we're still working on getting ready for showing.
Because in principle, before showing a ratio between far and near location, you should show the near location.
Right. Okay, sorry. Maybe I should have had that, your detector spectrum. But those results that I showed with the ratio were all for MINOS, which we've shown several times, those plots.
More? Yes?
Since you mentioned tests of CPT with MINOS, you look only for mass differences between neutrinos and anterneutrinos, or in general oscillation differences? Because CPT may not be necessarily linked to mass differences, but you may have, for instance, different decoherent rates, different damping rates, if it depends on some exotic models of. So what are you actually looking for? I mean, one is the delta M square minus delta M bar square, but do you look for other
Yeah, so no, I don't think. So there is what I showed in terms of transitions between neutrinos and antineutrinos. That would be a CPT violation. Is a bit different, but we don't have any models that we're thinking of testing right now. But we would be happy to take suggestions of models that we can test.
More? I see no hands. So let's thank the speaker once more. And I now call on Gregory Palazzo, who will talk on NOVA. 20 minutes. So I'll throw 5 minutes up for discussion.
Okay.
After 10 minutes, I'll show you 5 minutes left.
Okay.
And then we have some more.
Okay, so I'll be talking about the NOVA experiment, which is a long baseline neutrino oscillation experiment. We use accelerator neutrinos that are produced with an energy that peaks around 2 GeV. If you remember from Joel's talk, he showed the energy spectrum of the NUMI beamline, where it peaked at 2 GeV for NOVA, which is off axis. And we're at a baseline of 810 kilometers. So with this configuration of the energy in baseline, we're able to study oscillations that occur at the atmospheric regime. We use the NUMI beam, which is produced at Fermilab, the same one that Minos Plus uses, but we're at an off-axis angle so that we get a peak that happens at the 2 GeV. And the beam is running currently in the muon neutrino mode, but the polarity of focusing horns can be changed to that beam, and we can run in a beam that's primarily anti-muon neutrino. And so with those two configurations, we can study oscillations of muon neutrinos to the other neutrino flavors and anti-muon neutrinos to the other neutrino flavors. And so then by comparing the neutrino probabilities to the anti-neutrino probabilities, we gain extra sensitivity to CP violation and the neutrino mass hierarchy. So we're a 2-detector experiment. We have a near detector at Fermilab that measures the beam before it oscillates, and then a far detector in Ash River up near the northern boundary of the United States, close to the Canadian border, where we look for the oscillation signal to change in that beam relative to the near detector. And so our 2 detectors are functionally identical, and so that allows us to greatly reduce systematics because we have the exact same reconstruction efficiencies, selection efficiencies, responses in the detector. And so our results, when we get them, will be largely statistics dominated because of this. So for NOVA, we have plans to study 3 categories of physics topics. The key one is accelerator neutrino oscillation physics that uses the near detector and far detector to look for oscillation signal. But we also want to focus on just the neutrinos that are happening on our near detector to make cross-section measurements. And we also have a non-accelerator program in which we're planning on looking for supernova neutrinos if they ever happen, and magnetic monopoles and any other exotic behavior that might happen. However, since there's not a lot of time here, focus just on our main result, which is the accelerator neutrino oscillation physics. And so under that category, our 2 main objectives are to look for NUI appearance in the muon neutrino beam and the disappearance, the survival probability of muon neutrinos. And so with NUI appearance, we can measure theta 1,3, delta CP, and potentially the mass hierarchy. And for nu mu disappearance, we're sensitive to sine squared 2 theta 2,3. So sensitive to 2 theta 2,3, but not to the octant very well, and to the magnitude of the mass squared splitting. And then if we see a significant deviation from maximal mixing in our disappearance, we can combine that with the appearance channel to potentially resolve the octant of theta 2,3. So the NOVA detectors are liquid scintillator detectors. So what we have are these long PVC cells. They're as long as a semi-truck trailer, so that it's basically as long as you could put them to transport them to our detector site. And then you have one of these cells, and then they form a plane put side by side so that you can read out hits in one direction. And we have a wavelength shifting fiber running through that liquid scintillator and read out by avalanche photodiodes. Since we can only read out in one direction in this orientation, we then have another plane behind this that you can see here, in which all the cells orient the other 90 degrees with respect to that. And so, combination of hits in those two views then allows you to do 3D reconstruction of hits. And so, 77% of our detector mass ends up being active in this configuration. And in this configuration, we didn't get the following type of event topologies for the neutrino interactions that can occur. So for a new mu CC event in which a muon gets produced, we'll see a nice, long, almost straight track going for the detector. This shows one of the views. You get a corresponding plot in the other view and combine it for making a 3D event. And you see a little activity where the vertex is, and we're able to add in the energy from hadronic activity that came out of the vertex, plus the muon to measure the energy to 4 to 6%, depending on the type of resolution, depending on the type of new mu CC event that it is. For new events, we see an electron, and so we look for a cluster of hits that are consistent with an electromagnetic shower. And then for neutral current events, you could get various particles shooting out. The ones that are the biggest concern for us are pi zeros, since they produce an electromagnetic shower. And so you look for either, which isn't shown here, the case in which you have two photons that you could resolve, or you see a gap between the two photons that are overlapping each other to distinguish them. So you can see that there's a clear signature for what a muon looks like in a detector and what an electromagnetic shower looks like in a detector. So we devised multivariate techniques to identify clusters of hits, showers of events, tracks of events, or tracks in the events that look either like a muon or they look like an electromagnetic shower. And so for selecting new ECC events, we've designed two new ECC selectors based on multivariate techniques that loop over all the showers that we could identify, clusters of hits that we could identify an event and say, does this look like an electron? And then these multivariate techniques produce a value from 0 to 1, where 0 means it's very background-like, 1 means it's very signal-like. And so we do an excellent job of discriminating background and get 2 to 1 signal to background ratio with both of these selectors, even though they apply different approaches. And the point of having two selectors is just as a cross-check to make sure that we're getting consistent results. And something that's important to note is that in this background, it also includes our cosmic background. Our FAR detector doesn't have a lot of overburden. It's on the surface. Yet, because we have such a nice detector that's fine grain, we can really reject these cosmics. And so we get, in the case of one of these selectors, 40 million to 1 cosmic rejection, and the other one we get 20 million to 1 cosmic rejection. And so then we get a fraction of event for 1 year of data for cosmics. And so then we still maintain this 2 to 1 signal to background ratio, where background is everything else other than a new ECC event. We also have a selector based on multivariate techniques for selecting new mu CC events. What we do is look for a track that's very consistent with being a muon based on dx information, scattering information, track length information like that. And then we get a distribution from 0 to 1, 0 being background-like, 1 being very signal-like, and we get good separation between new mu CC events that are peak at 1 and background events. And so we first have an occlusive selector that just says, is there a muon there? Is it a new mu CC event? And those occlusive events have about 6% energy resolution. Since when we fit the energy spectrum, if we have a nicer resolution, we can fit the position of the peak much better. We decide to separate our samples out by resolution by applying a quasi-elastic selector. So basically, not necessarily having to be quasi-elastic, but just that you have an isolated track that carries the bulk of the energy in the event. And for those events, we have a selector, and when we select them, we get 4% energy resolution of those events. And for new mu-CC events, we get a 15-to-1 signal to background ratio. Our ratio is lower than what you could possibly achieve because all the new mu-CC events oscillate away because we have a very narrow band beam that's hopefully peaked as close as possible to where you have your oscillation maximum. And again, this also includes cosmic background in this estimation. So using these selectors and running through a proper analysis framework, we're able to produce sensitivities that will reflect what we'll get when we look at the data. And so the first sensitivity I want to talk about is our ability to resolve the mass hierarchy. So if you look on the plot over here, it shows observing the probability of nu mu's oscillating to nu e versus the probability of observing an anti-muon neutrino oscillating to an anti-electron neutrino. And so what you can see here is that we'll see different probabilities for neutrinos and antineutrinos, which can change based on which hierarchy you have, red being the inverted hierarchy or blue being the normal hierarchy, and the value of delta CP. And so for certain combinations of hierarchy and delta CP, you get degenerate probabilities, you can't resolve it. But for other values, you get clear distinction between the two hierarchies. And so for those values of delta CP, you can then plot, what's our ability to resolve the neutrino mass hierarchy. And so collecting our full data sample for the best case delta CP, we can resolve the mass hierarchy to 3 sigma. In the degenerate case, we really don't have sensitivity. And then for CP violation, as you can see from these contours, the separation is in hierarchy, not as much in CP. It's narrower along this ellipse, which represents different values of CP. And hence, we're not as good, but potentially, depending on the value of delta CP, we could get a measurement that's on the order of 1.5 sigma, and then when you add that with other experiments, the evidence for a non-zero value of delta CP can add up. In our disappearance channel, we'll make precision measurements of theta 2-3 and the mass squared splitting by looking at our energy spectrum. And so when you have maximal mixing, we'll get less events shown in red and also a more pronounced dip shown in red. And if you currently look at the values of theta 2-3 that are allowed at 90%, some of the more separated values that are allowed 90%, you see that with our full data set, we can resolve that. For instance, a value of sine squared 2 theta 2-3 equal 0.95 does not equal maximal mixing. And if we do see that, we can combine it with the appearance channel and then resolve the octant. And so this is showing our ability at how many sigma to resolve the octant as a function of delta CP. So in the case in which you have sine squared 2 theta 2-3 equals 0.95, we can on average over delta CP resolve the octant at the 3 sigma level. And then of course it gets weaker as theta 2-3 approaches 45 degrees. If it equals 45 degrees, you don't have an octant to resolve. Now, those are the sensitivities we have. I just wanted to mention that we are actually taking data, and we've been taking data since 2013. So when we first started taking data, we were still constructing our detector. And so the bulk of the data that we took is with a fractional detector. And that corresponds to about 1 E20 POT, protons on target, where our full neutrino sample is going to be 18. So 1/18 of our final neutrino sample. And near the end, or the beginning of fall of 2014, we started collecting data from the near detector. And then near the end of 2014, we started collecting data with our full detector readout. And so we've collected equivalent of 2 times 10 to the 20 protons on target, which is about 1/9 of the neutrino sample that we want to have for a 14 kiloton detector. So we want to make sure that our detector is functioning well. We've looked at cosmics in the far detector, look at distributions to make sure that the tracking is behaving properly, and we get great agreement between cosmic events and simulation and data, so it indicates that we're reconstructing track lengths and directions correctly, have the activity correctly simulated. We've looked at beam events, but only using limited hand scanning, so that can't blind us to do an analysis. One of the things we've done with this hand scanning to say this event kind of looks like a neutrino was to verify that we also see an increase of the number of candidate events happening in sync with the beam window. So it means our events are timed in. When we apply a timing cut, we'll actually select beam neutrino events. And we've looked at some of those events. Sorry, this is pretty bad with the projector, but they look like good neutrino events. So we've identified an event that looks like a new mu-CC event. It has that nice track and a little bit of proton activity there, presumably. That's consistent with what we see in simulations. So our events should be able to, our reconstruction and selection algorithm should work. And we see NUI-like events with a shower that looks like what we expect for an EM shower. So our detector seems to be functioning properly. And we've also taken near detector data, and here we actually have, since it's functionally identical to our far detector, the ability to see what neutrino interactions are going to look like in our far detector. And by comparing data in Monte Carlo, we seem to be doing a really good job with the tracking quantities that we've looked at, the direction, the track length, and even the shape of our selector of what's muon like and what's background like. It replicates features. And so what we're doing right now is looking at our near detector data, looking at those neutrino interactions, and making sure we really understand the different features that we see in that, so that when we look at our far detector, we'll know exactly what to expect with the neutrino interactions in our far detector. So to summarize, NOVA can potentially make some claim about the mass hierarchy, up to a 3 sigma determination for the best case of delta CP, and also with octant resolution, we can make a 3 sigma determination for the best case of delta CP and larger values or more deviation from maximal mixing that's currently allowed at 90%. We'll make precision measurements of theta 2-3 of the mass squared splitting. We're taking data with both detectors, and you should expect our first oscillation results this year. So thank you.
Thank you. So this talk is open for, please.
Looking at what you have shown, of course, for the NUI appearance, the pi zero is the most dangerous background. I've seen that now you have a lot of data in the close detector. You have evaluated experimentally what is your electron pi zero rejection?
So yeah, I probably can't publicly say what we have, but we are looking at our near detector, and so there is no oscillated NUI signal in the near detector, and so we're applying our selectors in the near detector, looking at those events, and comparing it to our Monte Carlo to understand our signal rejection of pi zeros. We've also independently done analysis looking directly for pi zeros, seeing if we can reconstruct the invariant mass of a pi zero. And so we've had an analysis that can effectively select pi zeros and reconstruct the invariant mass where it's supposed to be. So I think we have a pretty good handle on pi zeros, but we're still looking at our data, making sure we understand. I wanted to at this time say that our Monte Carlo says we have this rejection, and data we have this rejection, so not there yet. So we're still doing those.
You're working on it, but
yeah, we're looking at it. So right now, the reason why we're not presenting first results is because we're really focusing on looking at the data that's coming up.
Because without this evaluation, I believe that any oscillation results will be not solid enough.
That's right. So that's why right now, if you saw on that timeline, we only recently, basically at the end of 2014, got a near detector, and so we're looking at that near detector data right now. Yes.
Could you go back to your plot showing delta m squared versus theta 2-3? Yeah. Now, the uncertainty on, now presumably on the right-hand plot, this is a two-flavor analysis?
Oh, no. So we're using the full three-flavor probability in all of our fits.
Okay, so suppose I converted delta m squared 3-2 to delta m squared mu mu.
Mm-hmm.
So you have, like a 4% uncertainty on delta m squared mu mu, because it's essentially delta m squared 3-2. So this is after 6 years of running, is that right?
That's right. So this is our
Okay.
nominal full running.
So the Juno people are assuming a 1% measurement of this quantity, and you're showing a 4% measurement of this quantity. I just wanted to point that out.
All right. Well, so some of this will. I guess one thing is we need to make sure also we'll know what our final systematics are going to be. Right now we're putting in a little bit of an estimate on that. But I think if I recall that it's not actually 4%, it's more of a 2%. But still, that's 2% is still larger than 1%. But
More? Yes.
At the end, you told us that you expect some oscillation result this year. Then, for me, this means that you expect some positive oscillation result this year. But I want to tell you that there are models in which you don't see any oscillation signal. Thank you.
okay. Well, if we don't, then we'll see a lot of signal when we look at our muon neutrinos. Then, yes.
So some of the other experiments in your beamline, right, see some fairly significant differences with sort of the default Gini prediction for pion production, nucleon content. Can you say a few words about your strategy for taking the near detector data and retuning the interaction predictions?
Yeah, so some of our approach has been to, in the Gini package, there's parameters that you can re-rate to adjust the Monte Carlo. And currently what we've been doing there are adjusting parameters within Gini to re-rate our Monte Carlo and then comparing it to data. And I think one of the areas where we might be able to, if we do decide to tune that up, where we'd have some information that is looking at our track particle multiplicity. So we see that there is differences in the predicted number of tracks that are produced, particles that are coming out of nucleus from what you get in default from Gini and what we're seeing in our near detector. The one issue though is I'm not sure to the level that we will tune that, because since both of our detectors are exactly the same, when a neutrino interacts, it'll produce the same hadronic activity. And so if our model is off, when we do our study, it might cancel out in our ratio, in our extrapolation. Oh yeah, well that's one thing. So we are looking into our energy scale. So the one nice thing about being off axis is that it's very hard to change where the peak in our neutrino energy is located. So we have basically a standard candle to say what are the energy of these neutrinos. Yeah, no, that's right. But what I'm saying is I think that's where our primary concern of it would be, is to compare the energy of the events that we get and compare that spectrum to what we expect, because we kind of know where it should be peaking, and so that'll give us an idea of how sensitive our energy is to hadronic modeling, and we will correct for that. That's right.
More? Can I ask?
Yes.
So, what are future plans in the following terms? I mean, you're accumulating statistics, and eventually you will hit the systematics, so there's no more point in continuing. How many years more is, in that perspective, is beamline, your experiment? I mean,
So do you mean how long until we're systematics
Right.
limited? That I'm not sure of. I know we can run for 12 years and we still won't be systematics limited. One of the features is because one of the largest errors we could have is in our energy uncertainty. But since we know where the peak position is, when we fit our spectrum, it takes into account the fact that we know where the peak should be, and our systematics actually can reduce as we accumulate more statistics. So our systematics can actually decrease with data. Yeah, so I think for any proposal I've seen for extending NOVA running, we don't hit the systematics.
and the lifetime of your detector
That's
technologies
right.
is also so. You intend to run another decade.
Well, we'll see what we get.
Okay, so let's thank the speakers again. And we will now listen to Masashi, Dr. Yama, who will talk to us about T2K and J-part neutrino experiments.
Can I close this? You have 40 minutes. Oh, 5 minutes discussion. So I'll show you 5 minutes of 30 minutes, then we have some margin. 5 minutes. Yeah, okay. Okay. You have 35 minutes. 5 minutes discussion. Okay. First of all, thank you very much for organizers for giving us the opportunity to present in this excellent workshop. So I'm going to talk about the T2K and JPAC neutrino experiments. So first I would like to start from the status of JPAC. So JPAC is a Japan Proton Accelerator Research Complex, which consists of the 3 accelerators, LINAC, 3GeV rapid cyclosynchrotron, and mailing, which provides a beam to the neutrino, as well as hadron facilities. So actually, recently, those accelerator got some major improvement. So for the LINAC and the ion source, we first got the LINAC energy increase or recovery to the design value of the 400 MeV 2013. And also in the last year, we replaced that front-end system, that's the ion source and the RFQ, with a newer one to increase the peak current to the 50 milliamps. And altogether, LINAC now achieves that higher beam intensity and higher beam energy. And next is RCS 3GeV accelerator. In the beginning of this year, they successfully demonstrated that with a single-shot mode, 1 megawatt equivalent beam can be achieved without a significant loss or any problem. And with a reinforcement of the power supply for the continuous beam expected in this summer, they will try to operate RCS with 1 megawatt beam power in this next fiscal year, starting from April, later this year. 1 megawatt is actually a design value of that RCS machine. And for the 30 GeV main link, which provides that beam to the T2K, at the end of the last year, we were running at the beginning of this year actually. We are running with a 260 kilowatt or so. And the accelerator people tried to increase that beam power, aiming for the more than 300 kilowatt operation. But while I was preparing this talk last week, actually we got a big improvement of the beam power from the 260 to the 320 kilowatt. And for more than 1 week, we are running with this 320 kilowatt. And actually, we are not fully using the protons from the RCS in order to control the beam loss and radioactivation of the accelerator component. So now we are using 2/3 of the beam. That means that if we can control and reduce the beam loss, that about 430 kilowatt will be possible from this current accelerator. And in order to reduce the loss, installation of the additional compensation kicker magnet, injection kicker magnet, is scheduled in the next month. And we expect that this will further reduce the beam loss. And we can aim for the 350 kilowatt before the summer this year. And after summer, we try to increase the beam power to 400 kilowatt or beyond that. And beyond that, some midterm plan of the main ring is to replace the magnet power supply to achieve the shorter cycle or more increase the repetition rate to 1.3 second or close to 1 second. And the development of this new power supply is almost completed, and we are going to the mass produce this power supplies. And with this faster cycle, we are going to achieve the design value of the 750 kilowatt and maybe beyond in the 2017 or 2018. And we also are discussing longer term plan towards a multi-megawatt neutron beam facility. And there are several ideas under discussion. And one example is that to increase the energy of RCS to 3 dB to something like 3.4 or 3.6 dB to reduce the space charge effect, that which is one of the limiting factor in the current beam loss. And with simulation, it's shown that indicated that with increased RCS beam power, beam energy, we can reduce the beam loss, and we may achieve something like 1.5 megawatt in the main ring. Or even we are discussing that the possibility of adding another ring with 8 dB new booster between RCS and MR. And this is some conceptual design of the lattice and ring. And in this case, we may achieve more than 2 megawatt. And even this is a much longer time possibility, but we are also discussing a possibility of the new superconducting photon liner for the neutron beam. And this is one possibility that reusing the KKB tunnel after the super KKB project is completed. So this is not a JPAC, but a Tsukuba site. But conceptual study shows that we may have that 9 megawatt beam with more than 9 GeV proton energy. So we are discussing and making some longer term plan for the JPAC and the neutron beam in Japan. So now I turn to the experiments at the JPAC. And as you know, T2K is running at the JPAC. And actually, recently we have many experiments, spiral neutron search or hypercommunicon that will be covered by later talk. But test experiments and the new concept of the detector later window. So I will talk about these activities. The first, I will talk about T2K, which is the main largest experiment in JPAC. And T2K is a Tokai to Kamioka long baseline experiment using JPAC neutron beam and the super Kamiokan with a baseline of 295 kilometers. So combining intense proton beam from JPAC and high quality flux beam, high performance near detectors inside the JPAC, and gigantic high performance far detector Super K, we are studying precisely the neutron oscillation in the electron-neutron appearance and muon-neutron disappearance, and also we are measuring cross-section and also search for some exotic phenomena. So T2K collaboration is some 500 people from the 11 countries, and actually, from last month, Professor Nakaya from Kyoto University was elected as a spokesperson, and the former spokesperson, Kobayashi-san from KK, will become the deputy director of the Institute of Nuclear and Particle Physics study of KK. And we have international co-spokesperson, Chan Ki-jan from Story Group. So we started the physics plan from 2010, and until up to the end of the last year, we have accumulated 8.7 times 10 to 20 POT in total. And from the last year, we started operation in the reversed Hon current mode to provide the anti-neutrino enhanced beam. And we accumulated 1.8 times 10 to 20 POT in the last year for the anti-neutrino beam mode. So this is some example of the anti-neutrino event interaction at near detector. So we have magnetic field, so we can select the sign to select the anti-neutrino interaction in near detector. And we accumulated 40 fully contained in the physical volume events at the super K in the anti-neutrino beam up until within last year. And this is the first event in the anti-neutrino beam run observed at super K. And we cannot identify event by event the neutrino and anti-neutrino in SK, but this is the first event in the anti-neutrino beam. And now we are accumulating more data, and analysis of this anti-neutrino data is ongoing. So we expect to release the results soon, so please stay tuned. So for the neutrino oscillation analysis, we need several inputs like flux prediction and near detector understanding, systematics, and important neutrino cross-section models. So we fit the near detector data to constrain the flux and cross-section or interaction rate, and also improve our model of the neutrino cross-section. And using this fit result, we fit the far detector data and get the oscillation analysis. So from the upstream, so we have neutrino beamline, of course. And for the T2K beamline, recently in the 2013 to the 2014, we replaced all three horns successfully with remote handling, and we successfully established the remote handling procedure, which is essential for the long-term operation of this high radiation facility. And now we are able to accept the 500 kilowatt beam in terms of the beam line capacity. And we are now trying to increase that radioactive water and air disposal capability to increase this acceptable beam power to the 750 kilowatt. And one note is that the decay volume, inaccessible part after the operation, such as the decay volume or beam dump, were from the beginning designed and constructed for the capable for the multi-megawatt beam. So something like a 3 megawatt or 4 megawatt beam design. So we don't need a large facility construction towards that multi-megawatt beam. And for so for T2K operation, this is showing the beam stability measured by the on-axis event rate measured by the on-axis near detector, and this is a horizontal and vertical beam direction measured by the Ingrid on-axis detector and the mirror monitor. And throughout the experimental period, so far we have excellent stability for whole run. And here you can see that difference of the event rate between the neutrino mode and the anti-neutrino mode. And for the neutrino flux prediction, we are using the giant tree-based beamline Monte Carlo simulation tuned with the hadron production measurement, most notably by the NS61 SHINE experiment at CERN. And current uncertainty, flux uncertainty at the peak energy is about 12%, of course before the near detector constraints. But still, this flux understanding is improving. And for example, soon we expect to include the latest NS61 results that will bring us to this number to the less than 10%. And further, in future, we will use more data from the NSTX1, including the large statistical data with the TTK replica target. So this flux uncertainty will even decrease. And also, of course, we have the flux prediction for the anti-neutrino mode with a similar uncertainty that will be used in the coming anti-neutrino oscillation measurements. For the near detectors, we have two systems. One is called InGrid, that are located on axis to monitor the beam direction and stability. And the other one is that off-axis detector called MD280 inside the magnet, which was originally built for the UA1 and brought on SAM. And inside the magnet, we have pi0 detector and the fine-grain detector as an active target, sandwiched with a TPC as a tracking detector. And surrounding those are electromagnetic calorimeters and the muon detector instrumenting this magnetic yoke. So using this off-axis detector, we are constraining the flux and cross-section for the oscillation analysis. And we select the muon candidate as that using the high momentum negative track in the TPC. And the interaction occurred inside the fine-grain detector fiduciary volume. And we classify this muon charged current events into 3 samples depending on the number of the associated pions, 0 pion, 1 pion, and other sample to enhance the sensitivity to the exclusive neutron interaction channels or interaction models. So this is a distribution of the momentum and angular distribution of the ND280 charged current data set. And this is a 0 pi, 1 pi, and other subsample. And after some, so we constrain the rate and the cross-section parameters using those samples, and after some fitting, taking into account the correlation between the energy and the samples, we observe the good agreement between the model and the data distributions, and we use this information to for the prediction at the super K for the oscillation analysis. And one note is that the electron neutrino flux at super K can be also constrained by the muon neutrino measurement at the near detector, because they come from most of them come from the same parent particles, so through the kinematics of the parent particle, pions and kaons, we can constrain also the new flux. So this is resulting uncertainties after this using this ND280 fit result compared with the without ND280 fit for the one ring muon and one ring electron samples at super K. And this is uncertainty of the number of events, and this is uncertainty of the spectrum shape. And using the near detector measurements, the uncertainty is greatly reduced. And this is a table of the uncertainty on the expected number of events for new mu and the new E events. And the flux and cross-section constrained by near detector gives about a 3% contribution. And in total, we have 8 or 7% uncertainty on the predicted number of events. So far detector is a super K, and this is already very described by the talk by Nakahata-san on Tuesday. And we select electron neutrino and muon neutrino candidates, and this is showing the timing distribution for the selected neutrino event candidate, and we can see clear 8-bunch structure arising from the proton beam timing structure with a bunch structure with the JPAC, and this is a vertex distribution for the electron neutrino interaction candidates. And this is a 28 one ring E-like sample, which is a electron neutrino event candidate. And we can recently we improved the algorithm for the pi zero rejection, and actually this blue part is coming from neutral current interaction, which is dominantly pi zero. But as you can see, with improved new algorithm, we can successfully suppress this pi zero background very much. And you can also see that we have the very good, this magenta pink part is appearance signal. So we have a very good signal to noise or background ratio. And this is a 120 muon neutrino candidates, and also the purity of the muon neutrino is very good. Although the most part is oscillated out at that super K. So for the using these samples, we measure the oscillation parameters, and this is a new mu disappearance measurement result, which was published in the PRL last year. And this is the observed reconstructed neutron energy distribution compared with that Monte Carlo prediction without oscillation and with best fit oscillation parameter. So you can see that clearly this peak part is that disappeared due to the oscillation. And this is a ratio of the ratio to the unoscillated event prediction as a function of the reconstructed neutron energy, and we can see that the oscillation pattern clearly. And this is resulting oscillation parameters is that sine square theta 2 3 and delta m square. And this is we cannot see the other experiments, but so compared to the super K and minus, and we are providing a most precise measurement of the sine square theta 2 3 now. And for the in the last month, we submitted a long paper describing our nu mu plus nu e combined analysis for the neutral oscillation parameters. And we described the detail and present many results, but for just one example, two examples, we have a frequentist analysis and a Bayesian analysis. And so in the frequentist analysis with reactor constraint, we excluded some of the parameter space of the CP vibrating phase delta. So this colored part. And we, with a reactor measurement, we are starting to constrain this CP vibrating parameter. And with the Bayesian analysis, we provide some Bayesian probability for example, theta 2 3 octant and mass hierarchy choice like this. And we have slight favor of that second octant and normal hierarchy, but of course the significance is not so large. And this is again the delta CP credibility interval, Bayesian credibility interval, that also favors that delta was minus half pi. And we also have the other than the neutron oscillation measurements, we have a bunch of the cross-section measurements with near detectors, and this is some part of them as an example. And this is electron-neutrino cross-section measurements on the scintillator, which was published in the PRL. And this is a muon-neutrino inclusive cross-section. And also we have the ion and scintillator cross-section ratio measurements. Actually, this is a 3% measurement of the cross-section ratio by taking ratio. With that Ingrid on-axis detector, and also we have other measurements. And we have even more results, like neutron cross-section measurement at the far detector super K. And thanks to the unbiased trigger based on the GPS timing of the beam spill, we can select some low energy events and study the neutral current interaction at the far detector. And just last week, we submitted some neutrino mass limit from the relative time of flight and relative time of flight dependence of that on the neutrino energy, and put some limit on the neutron mass. And also we have the disappearance measurement search with a near detector for the electron neutrino, and this is accepted for the publication in a PRD. And we have a poster presentation by Stefania on this, including this search for the disappearance, new disappearance, short baseline oscillation studies in the T2K. So if you are interested, please visit this poster. And of course, more results are already published or are coming soon. And we are now accumulating the anti-neutron beam. So also the results with anti-neutron beam data will come soon. So please stay tuned. And in future, first near future plan, before this summer, we aim for the world best anti-neutron oscillation measurement. So this is an example. So the new mu bar disappearance sensitivity with 1, 3, 4, 5 times 10 to 20 POT, overlaid with the minus new bar disappearance result. So with the data set anticipated before this summer, we will we plan to provide this kind of the anti-neutron oscillation measurements, and also the new E bar appearance search. And in 1 or 2 years from now, we continue to improve the oscillation parameter measurement with a neutron beam. And for example, current kind of some tension with a reactor data measurement of theta 1,3 and TTK new appearance measurement remain with that more data or not is interesting, I think. And also, of course, that with anti-neutron beam, we will search for the electron anti-neutrino appearance, and we expect this kind of the POT with that 400 kilowatt beam. And in the longer term, we soon published in the PTEP journal. This is a journal published by JPS, and with that our study of the future sensitivity with a full data set of TTK. And our goal is to search for the CP variation with up to something like 2.5 sigma level sensitivity, and precise measurements of the oscillation parameters, and of course various neutrino and anti-neutrino cross-section measurements. And for the oscillation measurements, we expect that combination with NOVA and Super K will enhance the reach. This is an example of the delta chi-square to the CP conserving case, and red is the T2K, and blue is a NOVA expected sensitivity, and combining T2K and NOVA, we will have that enhanced sensitivity. Okay, so using the remaining time, I will also just briefly introduce other neutrino experiments at JPAC. So as I said in the first, in addition to T2K, we have several programs ongoing or proposed at the JPAC facility. One is the sterile neutrino search at the JPAC Materials and Life Science facility. And recently, this sterile neutrino experiment got stage 1 approval from the JPAC PSE. And we have a couple of the neutrino test experiment. One is that test experiment to measure the neutrino cross-section using the new 3D grid-like scintillator neutron detector with a water target. And the other is that emulsion-based test experiment. And also we have a new letter of intent for the new detector called the new prism in the JPAC neutrino beam line. So new initiatives are emerging in the JPAC neutrino experimental facility. So I will briefly explain those experiments. First is that sterile neutrino search, now given the experimental number E56. And this is not using the, this will not use the beam from mailing, but from the 3GB RCS and on the neutron production target for the primarily for the material science. But the idea is that with this 1 megawatt intense beam with a 3 GeV energy, we will have we will produce that many pions and muons, and thanks to this pulsed beam timing structure, we will have the almost pure neutrino from the muon decay at rest if we wait for some kind of that 1 microsecond or so. So using this neutrino from the muon decay at rest, they will search for the new EVA appearance. And this is some expected neutrino spectrum. Red part is that possible signal. And using this energy distribution, we may find some clear evidence of the stellar neutrino. And so this is the expected sensitivity, 90% confidence level sensitivity with 5 years running of the 1 megawatt beam. So this will cover the LSMD region. And for the detector, this is a new EVA appearance measurement. So they are planning to use that gadolinium-loaded liquid scintillator. And this is, of course, a very established technique and for the reactor neutrino experiments. And they have collaborators from the WHO diabase experience. And one note is that this detector will be located at the maintenance area of the MLF facility. So this should be kind of the movable while maintenance is ongoing. But they got stage 1 approval, so they are now designing the detail of this detector. And so the test experiment, one test experiment is that so-called Wagashi experiment, which is use a 3D grid, this kind of the grid scintillator detector. And the idea is with this kind of the structure, it's hard to see, but combining this and ordinary horizontally or vertically placed scintillator combination, we can realize that the large angular acceptance with less material. So with this detector putting inside the water, we can measure the water target cross-section on the water target. Something like the fraction of the water is at 80%. And with large angular acceptance, thanks to this structure, we can reconstruct the track with a perpendicular direction. And putting some ion MRD, we can identify the muons. And this 3 millimeter thick scintillator is produced at the Fermi-Lab scintillator production facility last year. And the light yield is confirmed to be sufficient, so we are now designing and developing the detector components. The other test experiment is that feasibility test of the immersion technique in the JPAC neutrino environment. And long-term goals measurement of the neutrino cross-section with immersion, and also the possibly sterile neutrino search. But as a first step, we put some immersion films in the near detector hole and testing the background environment and the feasibility of this future neutrino experiments using the immersion in the JPAC neutrino facility. The last one is that so-called new prism, which is an idea of the utilizing this, because we are running with that off-axis beam. So if we dig the deep hole and measure the neutron beam at various off-axis angle, and combining this, using this dependence of the neutrino energy, depending on the position, we can extract the neutrino energy information and correlate the neutrino energy to the final state observable without with less dependence on the neutrino cross-section models. And also this kind of detector will be able to study the stellar neutrinos or unique cross-section measurements, and also the enhanced sensitivity for the long baseline neutrino oscillation measurements. So letter of intent was submitted to the PSA last year, and the people are working for the more concrete proposal. soon to be submitted again to the JPAC PSC. So let me summarize my talk. So observation of the electron-neutron appearance by T2K has opened the door to the CP asymmetry study. And already we are constraining the limits on the delta combining T2K and the reactor experiments. And T2K will continue to lead the neutron oscillation study in future. And we expect to release the first anti-neutron oscillation results soon. And now we are collecting data with a 320 kilowatt and higher intensity expected soon. And we are making plans for the JPAC beam power increase to the design value of that 750 kilowatt and beyond, maybe beyond the megawatt. And in parallel, we are seeing the new neutrino experiments activity in the JPAC with international collaborations. And so now we have very active people proposing new experiments. That's good. And of course, we have a next generation large-scale experiment, that's the hypercamiokande, but that will be given by Shioza-san in a later talk. Okay, thank you.
Thank you.
Slide, you say that you can go up to 430 if you remove beam losses. But as you say here, the nominal value is 750 kilowatts. When do you think that you will go to 750 kilowatts?
Okay.
And if I understand well, you want to go there with the present accelerator configuration.
Okay, so in the present accelerator configuration, maybe 430 or 450 kilowatt is the limit. And in order to go to the higher intense beam power, like 750, we need to replace the magnet power supply of the main ring. And we are going to do that in the next few years, and we anticipate that this replacement happening in 2017 or 2018.
So there's a lot of debate about how important it is or unimportant it is to have charge separation in your near detector. So I'm wondering, for T2K, your anti-neutrino running, are you going to use the wrong sign events in your near detector to constrain your far detector prediction?
Yes, yes.
Yeah. Because I was just noticing, because you had said that the nu E prediction for your far detector, you're using the nu mu events from your near detector rather than the nu E events.
Yeah, so yeah, for the anti-neutrino mode, of course, we have the large contamination of the neutrino. So yeah, we measure both that nu mu and nu mu bar in the near detector. Thanks to this magnet, we can sign separate. So yeah, that will help us for especially in the anti-neutrino data analysis.
Thanks.
More? Yes.
Okay, first of all, let me congratulate for the high level of this presentation, as name also for Mauro. Then I have two news, one good and one bad, in my opinion. The bad one is that in the sterile experiment in which you belong, you are not really checking the LSND experiment, but the Carmen experiment. So the result of Carmen was negative. So I expect you to find the same result. The good news comes from the anti-neutrino run in the same model that does not predict oscillation signal in nova. The same model will predict more electron neutrino in your anti-neutrino run. In Padova we say, troppa grazia Sant'Antonio.
Okay, actually, I'm not a member of this experiment, first of all, okay. So I'm presenting on behalf of this experiment, but yeah. Thank you very much for your comments.
Can I ask you a question?
Yep.
Page 9
Page 9.
on power increase. So,
Page 9? Long-term
this
plan?
boost,
Yeah.
right.
This one?
The booster, yeah, so HEV booster ring. So this, you will inject then in the main ring the HEV.
Yep.
So,
Yep.
so reduce
special charge effect.
and then you will be able to go to 2 megabytes, you said. Yeah. And then eventually D9. So when you have this, you're preparing now the decay tunnel and the dump to go to very high powers, you said. But what about the target itself and the board?
Yeah, that's another story, of course. And right. So I forgot the exact number, but yeah, we so I should have table of that. And yeah, for some of the beamline components has a capability to 1.5 or 2 megawatt, but apparently, as you said, that target and horns as such, we need also the development to reach this more than 1 megawatt beam.
And another at 20 page 25, you say that you have of order 7% systematic errors now.
Yeah.
Yeah, but then a few pages earlier you said something like 12 or 10%.
Oh, yeah. So that's a uncertainty of the flux before the using the near detector constraints. So with using the near detector, we can correlate the flux and the cross section, and we can reduce the uncertainty of the supercave prediction.
So what is this 10-12% figure? What is that?
That's for example, yeah. So absolute flux at the near detector, uncertainty of. It's based on
the difference between 12 and 2.
Yeah. So this 12% is based on the Monte Carlo simulation with the tuning to the hadron production data.
Right. So let's thank the speaker again. And we will now have the last speaker for coffee, which will be given by.
Oh, sorry. I think I need
on
to.
some novel ways for neutrino mass generation.
I'll do it. Can somebody tell me, since the previous speaker, which is the system that, because is it where my talk is? Because I uploaded it yesterday.
Do we have an expert?
There was a.
I don't know more.
Me neither, because the previous, because she. Okay. Where is the? Because I uploaded it yesterday. So where was the? Sorry about that. Well, let me start by saying, well.
He's doing. No, he's.
25.
Yeah, so 20 plus 5, I suppose.
25 and the 5 minutes discussion.
Yeah.
So I will give you after 15 minutes.
Well,
5 minutes
perfect.
more.
Great.
We have some more.
Perfect. Thank you very much. Let me thank the organizers, first of all, Mauro Mezzetto and Marco Lavade, for their kind invitation. Oh, he's coming. Good. Okay. And the full screen is... yeah, that one, isn't it? Yeah. Okay, great. So, I was assigned this subject, so you can ask your fees back if you're not happy. Now, let me, since it is we've had excellent presentation on real physics in the past 3 talks, so let me now take you up to heavens, all right? Because I'm a theorist. But not so much up to heavens. I mean, let me tell you one thing. I mean, we don't know anything about what kind of mass a neutrino has so far, because we haven't measured the absolute mass of the neutrino. Neutrinoless double beta decay would be one decisive experiment if the neutrino is Majorana, but neutrino could be Dirac. Moreover, with an standard model, the neutrino is massless, and the only mechanism we know so far to give, the established mechanism to give masses to neutrinos is the seesaw, which requires the existence of a right-handed neutrino. However, in this talk I will discuss mechanisms beyond seesaw, which could be could be linked to some geometrical origin of neutrino masses. And when I mean neutrino masses, I will include right-handed neutrinos. So maybe what I will discuss today applies only to right-handed neutrinos, but I will tell you about how you can in principle test it. So I was motivated by, in fact it was mentioned by Dr. Coelho in the first talk, that there are theoretical frameworks like the standard model extension where there is CPT and Lorentz violation in the early, which in my view could exist in the early universe but have been completely washed out today. Another important aspect of the geometrical origin of the mass that I'm going to discuss is the so-called torsion. The geometry may have, torsion is a field, in fact it's an action-like field which exists in some string theory models, which could be, through its interaction with neutrinos, could give them masses. So I will divide the talk in two parts. The first is coming from this part, where we shall see that some string-inspired theory models which are associated with backgrounds of this torsion and are linked to leptogenesis in the early universe that I will not talk about in detail, may be responsible for giving a mass to neutrino through novel interaction of neutrinos and axions. So in this particular case, two dark matter candidates may be interacting together, and there is a special novel interaction between neutrinos, which could be right-handed neutrinos, and axion fields that in principle could be tested. And the second the second part, very briefly, I will discuss alternative ways where there is a Lorentz violation as an ultraviolet regulator, but it seems that the screen cuts a little bit down, I don't know why, but fine. It cuts, there is a Lorentz violation, which however occurs at a given scale, which is removed. So, if you violate Lorentz symmetry and CPT, the CPT operator within the standard model extension is a well-defined operator which does not commute with the Hamiltonian. If you apply this, and this is my motivation, I will not really stay on that, but if you apply this mechanism to the conditions of the early universe, you may obviate some of the Zakharov's condition. For instance, you don't need a CP violation necessarily to generate the biogenesis. The CPT violation itself may be generating biogenesis in the sense that there will be different dispersion relations between particles and antiparticles. That mechanism applies only if the neutrino is Dirac, not Majorana. Majorana is its own antiparticle, therefore there wouldn't be any difference between its own energy. However, if there is a Lorentz violation in geometry in the early universe, which is washed out today, it can act as an extra source for three-level CP violation, and not at one loop, but occurring at three levels through the decays of right-handed Majorana neutrinos to Higgs and ordinary neutrinos, and therefore that's how the geometry operates. And this is, however, these backgrounds can also, the fluctuations about those backgrounds can give masses to neutrinos, and this is what I'm going to talk about. So, the standard model extension in the fermion sector essentially consists of taking operators and giving verbs. So it's a spontaneous breaking of Lorentz symmetry through some microscopic mechanism. And the terms that I'm going to concentrate for this talk are this, which violates only Lorentz, or this, all right, which violates both CPT and Lorentz. This comes with a gamma 5 matrix, and it could come from some chiral currents. And this is actually what the torsion term would be. The second models, which in the second part, I will be concentrating with higher derivative Lorentz violating operators, in which you see here is just a spatial derivative, and this is the scale of Lorentz breaking. So I will discuss Lagrangians like this, which could also have a microscopic origin. And the important point here is that, as we shall see, the masses here can come from fermion self-interactions, which could be usually weak. For instance, it could be a Nambu-Jonah-Lasinio interaction, which, if you didn't have those terms, would require a strong coupling to generate dynamically the mass, because that was the original model of Nambu and Jonah-Lasinio for breaking chiral symmetry. In the presence of these terms, you will have a term which is weak. And also some gauge interactions. This doesn't have to be the electromagnetic field, but it could be a vector field in the neutrino sector. Eventually, I will remove this regulated to infinity, but the masses times the coupling, because the mass is proportional to a product of the mass times the coupling, will be finite. So that's the idea. So let me discuss first the torsion. What do I mean by this? So in the early universe, you may have torsion. In the gravity sector, torsion couples through this covariant derivative, which plays the role is like a gauge field, but pertaining to like the gauge connection, but pertaining to the gravitational field. Essentially, all it means is that if you have a fermion in a gravitational background, if you have torsion, you have an axial coupling like this, which is associated with the antisymmetric part of the connection. If you don't have torsion, the Christoffel connection is always symmetric. And this is important because this is like, if there is a constant torsion background, this violates, as you see, C and CPT, because this is of the same order as the SME coefficient. And there are examples of constant torsion backgrounds in string theory, for instance. In the gravitational sector of string theory, apart from scalar and spin 2 parts, which is the graviton and the dilaton, you have also a spin 1 antisymmetric tensor field, which is like a gauge field, but with 2 indices. And because of this gauge symmetry, it appears in the Lagrangian only through its field strength. Essentially, this star means contracting this with the epsilon symbol. So this is a Bianchi identity. That's the Lagrangian. So forget about string theory. I can tell you that you have this extra field, which is associated with the field strength of an antisymmetric tensor field, spin 1, plus the curvature. You can absorb this inside in a generalized curvature, and because this is antisymmetric, this is not symmetric, and that's what plays the role of torsion. In 4 dimensions, this is like an axion. It's a gravitational scalar, so essentially your theory is having a graviton plus this gravitational scalar field. And this is a degree of freedom which pertains to torsion, so when you couple it to fermions, you couple the fermions with this term, and eventually you have theories where this term is, remember, this is the derivative, the action is the derivative of this scalar field. In cosmology, you can only have time derivatives, and therefore the torsion could be constant in space. That violates Lorentz symmetry, because it's a constant vector, it's spontaneous, it's an innocuous violation. There are solutions in string theory where this action is linear in time, or if you have fermionic currents in the early universe, again, there are the gravitational action is constant, is linear in time, so its derivative its rate is constant, and eventually may decay through some phase transition. Today, that's why today you find it very small. So the idea is, if you have a constant rate of this action, you have a constant background here, and that's why you have a SME extension. This is the numbers that you would need are obtained from leptogenesis, because essentially if you have right-handed neutrinos, up to 1, 2, and 3 terms of the standard extensions of the standard model with the right-handed neutrino, sterile neutrino communicating with the Higgs sector. This is the dual of the Higgs field, and this is the lepton doublet. The torsion introduces a background. In the presence of this background, decays of Magellan neutrinos like this, of the right-handed Magellan neutrinos like this, are CP vibrating at 3 levels, and you can tune the magnitude of this, which is free in string theory, so as to generate leptogenesis. But you don't want to have a background. You may want that quantum fluctuations to wash it out, and this brings me to the mass generation through anomalies, actually, which is a novel. So quantum fluctuations may wash out completely any Lorentz violation, so don't look for it today. But there is one effect which is associated to axions and coupling to this field. So, and as I said, this massive mass generation is through anomalous terms. How? You have this term, S is this age term, in our case, the derivative of this action, which eventually you implement a constraint, and actually when you have torsion, you integrate out. Torsion is a non-propagating field. And when you integrate out the constraint, you have these terms, which by partial integration, you have a B times the derivative of the axial current. If you have anomalies, the derivative of the axial current is not conserved. It's given by the FF dual of the gravity. And this is the first term. So the torsion amounts to having a gravitational sector with this form. Now, usually, whenever you have actions, you have a shift symmetry. The action can be, and this is a pseudoscalar, it can be shifted by a constant, and this is the total derivative, and that's fine. If I want to break the shift symmetry, and that's our mechanism, first by coupling this gravitational torsion action with an ordinary action field that you have, and you have a refractive index for the neutrino, all right? You are allowed to have a conversion of action into a pair of neutrinos. This will slow down the neutrino. You don't have to give to the action event, but this is the ordinary action that creates a medium where the neutrino propagates. And in this medium, the neutrino is slowing down. How? You can shift some variables here, change variables, and actually that's your action. So you have an action, the real action field now, coupled to this neutrino, which could be a right-handed neutrino, plus this term. This comes from the top, so this comes from the gravitational part. And this is one loop order. So you have a neutrino with an anomalous graph. It's a 3-loop graph. Nothing else. But because of this coupling, because of this breaking of the shift symmetry, I can generate a mass for the neutrino, which depends on the ultraviolet cutoff of the theory, of course. You can get some numbers, because both these values, the gamma, the mixing terms are free parameters, and they have a couplings here. And you can get warmed up quantum neutrinos, which are interesting. They can be constrained by the fact that if you have a decay of the neutrino to the ordinary lepton sector, mixing with the ordinary lepton sector, you can, by the fact that you don't observe this line, you can constrain the mixing enormously. And I don't need the mixing actually for the mechanism of mass, and you can have other terms. If you have more actions, than one, like you have in string theory, you don't have only one action, then you can even get cutoff independent from n equals 3, you can get cutoff independent mass. So that means that I have found an anomalous way of generating a mass without beyond seesaw, just by coupling the neutrinos to an action field, breaking the shift symmetry. But I needed the gravitational action, the torsion. I needed to modify the geometry, which I had. My final part is, so this is the first thing, and for experiments, you should look for these terms, all right? Action, conversion to right-handed neutrino. First of all, you have to find the right-handed neutrino and then look for this, but I'm not an experimentalist. Second, these models, they can be, you see the Lorentz violation here arises from this fact, which is not a covariant derivative with space-time Laplacian, but only space. And you can have them either in the so-called Lifshitz theories, which are models in which they try to generate ultraviolet well-behaved gravity, or you can have it trivially in string theory in this model. This is our brain world. It's a 4-dimensional 3 plus 1, and then you propagate the power. In string theory, you're allowed to have brains. You're allowed to have wrapped up brains, and they provide a medium. It's a long discussion why this doesn't overclose the universe, but it doesn't. The reason is why when these brains come near the brain world, they become more or less massless. If you have a neutrino, which is an open string attached to the brain, according to this view, interacting with this defect, then this situation as the neutrino propagate distorts the space-time. These are massive defects. You only look at this. So eventually this breaks Lorentz symmetry because of the recoil of the defect, but the mass scale here is the string scale or the Planck scale divided by the density of defects. So that's more than enough. Divided by the density of defects. So you notice here that in order to have trans-Planckian scales in the Lorentz violation, I don't need to go beyond Planck where I don't know anything, where all full quantum gravity effects. But I just need a very low density of defects. That's how I remove my cutoff, which I was saying. And then you can prove that the coupling, the dispersion relations at this scale of the neutrinos are like that. If they are in the infrared, when the momentum is much, much smaller than the Lorentz violation scale, or much higher than the Lorentz violating scale, because remember, in string theory, this doesn't have to be Planck. It could be even TV. So you have a freedom in string theory to where you are. The only Lorentz violation is, of course, where the momenta are comparable at the mass scale. Now there, depending on the sign of these parameters, because B is a parameter of the model here, you can even have superluminality, all right? But very small. In principle, in the string model, you don't. It's always subluminal. But this is something to have in mind. The important point is that when the mass goes to infinity, i.e. the density of the defect goes to 0, the masses are finite. And how you get the masses? the usual, you integrate out the fermions, you have the one loop effective potential with respect to the self-interactions that you have a scalar model, psi bar psi square, for instance, the simplest one. You linearize it with a scalar auxiliary field, and you end up with this auxiliary field, which becomes dynamical, but in the limit when you remove the mass is non-dynamic. You only consider the mass is the value of this field times the coupling. And they always appear with this mg square, all right, times a number for various values of this parameter. You can always take the g to 0 and m going to infinity, which is supported by the string scale as well. And therefore, it's an innocuous violation. The mass is finite. The final thing, you can have flavorless oscillations. If you have two flavors here, again, the mass is similar, but you have a mixing angle here, again, which are finite. The only important point of the oscillations is this one. If the scale was finite, which could be in a string scale, in a string limit, even if it is Planckian, the oscillations will not have the standard L over E term, but an energy over E as well, not 1 over energy. And that's important. You could really, by not observing the energy dependency of the oscillation today, you can tell us what the M is. You can go beyond Planck, but as you remember, the M is the M Planck over the density of defects. It doesn't mean anything to tell. It's not that the model is ruled out by being beyond Planck. You only constrain the density of defect in this particular case. So that's the important point. If you, of course, remove it and you view it as a regulator, you get the standard mass difference on the oscillation. And you can extend that to Majorana fermions, there's no problem here, or to the seesaw type extensions. And you can generate this Lorentz violation to generate the Dirac masses. So here, instead of embedding it in a grand unified model, you just use this generator. And to finish, the interactions don't have to be only scalar for fermion interactions of the neutrinos, but there could be some vector interactions as well, or current. In this particular case, the mass generation occurs by having the propagation of a photon, of a vector field, is not a photon for Majorana fermions, propagating in this background. So this is the Schwinger-Dyson equation. And the important point here is that the mass is non-perturbative. You see, it's exponential of 1 over the coupling square. But again, I can get the coupling, the limit, the finite limit to 0. This model, and I think that's my ultimate transparency, this model is not good in generating a Dirac mass. You can only generate a right-handed Majorana mass, but that's fine. You may just have a massive right-handed Majorana neutrino, which then interacts with the rest, sterile neutrino. But the mass is non-perturbative, and the mixing is, there's no mixing here, it's pi force. So, what have I done here? I was motivated by detailed models for leptogenesis, where early universe CPT violation and Lorentz violation may play a role. But such models entail torsion, which essentially is a pseudoscalar field, is a gravitational action, whose fluctuations can generate a mass for the neutrino via mixing of the gravitational action with an ordinary action. So I have two pseudoscalar fields, one geometrical in origin and one the ordinary action. And the breaking of the shift symmetry introduces a Yukawa coupling between the right-handed neutrino's chirality preserving mass, psi bar Majorana C, psi C coupled to actions. And then you generate a mass. The other thing are Lorentz violating scenarios. This could be of relevance, the self-interactions that I discussed and how mass is generated could be of relevance to some ideas that Remo Ruffini and his collaborators and myself are pursuing now, because they may play a role. We found that the structure of galactic core and halos may have, if you assume warm dark matter there, you may be able to describe correctly without the need for any other extra. So, I think I can leave you with this picture. Very good.
Thank you very much.
Thank you.
Who's that?
This one.
What do you mean with the vector field?
I have an interaction. It's not a gauge because it's Majorana, but they have a vector self-interaction. And this could be even very massive, so as when I integrate it out, I get a current, I get an ambujolar Arsenio, psi bar gamma mu gamma 5 psi square. So vector sterile neutrino self-interaction. So you have is in the sterile sector, is not an electromagnetic field, is not a gauge field, but they have these self-interactions. We found that if you add these self-interactions vector type, with the strength which is of the very weak, you can enlarge the core radius to acceptable phenomenological levels by astrophysics. If you don't, you cannot. So it's an interesting next work. But that's why we were motivated by how masses are generated in this way.
Okay. So let's thank the speaker again.